get started. Welcome to Space Drafts. We are the local chapter of Astronomy on Tap, which is an international organization where we give science communication talks in bars across the world. At our local Space Drafts, we are all members of Stewart Observatory at the University of Arizona, some postdocs and grad students. And we have a couple of exciting talks this evening. We're a little bit off cadence, so we're a bit lightly attended. We normally meet every third Tuesday of the month, so come check us out when we're back on that normal schedule. The reason that we have moved it is because this is the Rubin special. So we have two scientists from the Rubin Observatory that are going to be teaching us a little bit about astronomy. So we have Aaron and Agnès. Aaron is from NSF's NORLAB, and Agnès is from the SLAC National Accelerator Laboratory. So we will have the two talks. In the middle, we will have a 20-minute intermission, and I will come back with some astronomy in the news. And one last thing is we are next to train tracks, and we will almost certainly be interrupted by a very loud train. So anytime you hear a train, raise your beer and say choo-choo, and drink your beer. Also, one last thing is that we have a couple of trivia questions peppered throughout the talks. So our speakers will call on you if you get the answer right. Come up and see us at our merch table behind me here to pick out your free item of merchandise. And if you don't win the trivia, come check out our merch table anyway. So we'll be working that at intermission. So Aaron, you can come take it away.
Okay, right. Thanks a lot for the introduction. Yeah, I'm Aaron Meisner. I'm a staff astronomer at a place just down the street here in Tucson on the east side of the U of A campus, right near the astronomy department of the U of A, called NSF's NORLAB, which is a very long acronym that stands for National Optical-Infrared Astronomy Research Lab. And basically what we do is we manage a lot of the premier ground-based optical and infrared telescopes in the US, for example, and also in Chile, but that are managed by the United States. So we're kind of like a US national observatory in a way. And within NORLAB, I specifically work on the Rubin Observatory project, which I'll talk about a little bit at the end of my slides, and then Agnès will discuss in more detail.
It should. It was.
Do I need to turn it on?
It was on. It's on. There we go.
Okay, thanks, Tim.
You bet.
Okay, now it's on. Sorry about that. So yeah, today what I'll be telling you about is some projects I've been working on relating to crowdsourcing the hunt for nearby worlds, which involves large data sets and citizen science, kind of the type of stuff that we imagine doing in only a couple years' time with Rubin, but on an even larger scale because there'll just be even more data from Rubin and its LSST survey. So the scientific motivation, the scientific background here is that one of the most timeless quests in all the history of astronomy is to look for new planets in the outer realms of our own solar system. And so there's a long history of this, and it's generally not gone very well in the sense that lots of people have liked to hypothesize about potential planets. You might have heard this called Planet X, for example, or Tyche or Nemesis, but basically none of them have come true. And so only one planet in the solar system was ever discovered by a correct mathematical prediction. And so I guess I have my trivia question very early in the talk. But fill in the blank, discovered in 1846, is the only planet in the solar system found by a correct mathematical prediction. And the options here are Uranus, Neptune, Mercury, and Saturn. So we'll get back to that, I guess, at the end. I would note also that Pluto was a chance encounter, a chance discovery in 1930, which was based on faulty predictions of a new planet, which I think at the time were referred to as Planet X. But nevertheless, not everyone is completely discouraged by all the past failures of predicting and discovering planets in the outer solar system. Some people continue to try this. And most recently, there's been a lot of buzz about what's called the Planet 9 hypothesis. So you can think of this as being something like Neptune, but about 20 times further out in the solar system relative to Neptune, which is already quite far away in the solar system compared to the Earth-Sun distance, for example. The other one that still remains plausible, at least to some extent, although it's less scientifically well motivated. I refer to as Planet X, and you can think of this as something like Jupiter, but 5,000 times further away from the sun than Jupiter is, so about 25,000 times further away from the sun than the Earth is. And one key thing to note about both of these scenarios is that in both cases, the hypothesized planets would be in the very cold outer regions of our solar system. So on the theme of cold, there's this continuum going from normal stars like our sun, which you call main sequence stars, all the way down to very cold giant planets like Jupiter, where Jupiter has a temperature of about 135 Kelvin here versus about 5,800 Kelvin for our sun. And there's a continuum everywhere in between, so going to the lowest mass stars, those are called red dwarfs. But then in between the smallest red dwarf stars and the largest giant planets are something that we call brown dwarfs. And they're these kind of enigmatic cosmic objects that defy categorization, right? You can't really explain them other than to say they're in between stars and planets. And the temperatures of these objects really influence the detectability and the way we've gone about discovering them over the history of astronomy. So, as you might guess, stars like the sun are readily detectable at visible wavelengths, like the wavelengths that we see with our eyes. But as you go to brown dwarfs and planetary mass objects, these are much colder and they emit the peak of their radiation in the infrared, so like wavelengths about 10 times longer than the peak wavelengths for the sun. These are also similar wavelengths to, how sometimes you see infrared cameras looking at people, right? That's because people are kind of in the same temperature range as some of these cold planets and brown dwarfs. So these things are glowing, but only very faintly and in the infrared. Luckily, in recent years, we've had NASA WISE mission that stands for Wide Field Infrared Survey Explorer. It's a satellite that's providing an incredible new view of the infrared universe. It's a satellite in low Earth orbit, which you can see here every 90 minutes. It goes around the Earth, basically circling around the poles, and it's riding along the day-night line, so it's constantly looking outwards from the Earth to observe the universe. It's actually observing right now as we speak. Every 10 seconds it grabs another 2 1 megapixel each images, which is pretty awesome to think about. It launched in late 2009, and it was originally only spec'd out to last for 6 months or a year, but it's still going 12 or 13 years later, which is pretty amazing. This is just illustrating how WISE scans the entire sky over time as the Earth goes around the sun, and as the satellite goes around the Earth, it's sweeping out these big circles, and these big circles gradually paint in the entire sky and cover it many times over. So with WISE, by now, we've seen the entire sky something like more than 20 times, which is really an amazing time domain data set. Time domain, I'm sure, will be a great connection to make with Rubin and LSST in the latter part of this talk and for Agnès' talk. So yeah, with this revolutionary new view of the infrared universe, this has come some really amazing and historic discoveries. This is kind of like a schematic diagram of the very nearest neighborhood of our sun in the Milky Way galaxy. And there's some relatively familiar names here. So Barnard's star, it's one of the closest stars to us. It's a red dwarf star. It was discovered in 1916, so more than 100 years ago. And then others you might be familiar with are Alpha Centauri and Proxima Centauri. Proxima Centauri being the closest known star to the sun. And that was also discovered in the 1800s or 1917, again, more than 100 years ago. But then there's a few other of these very deep red dots meant to symbolize their cold temperature that were only discovered only a handful of years ago using this new WISE data. And the reason they were overlooked for all these centuries, even though people were constantly scouring for new neighbors of the sun, is because they're so cold you can only see them in the infrared. And so these special objects are now known as the third and fourth closest systems to the sun, behind only Barnard's star and the Proxima system. And so these are called WISE 1049-53, also known as Lumen 16AB, and WISE 0855. So these were both discovered in 2013 and 2014, so very recently by the standards of everything else in this picture. Oops. Let me see if this video will play.
I need to back up one more and advance again.
Oh, it was playing. Yeah, I think I got impatient with it. There we go.
There we go.
So everything in the universe is moving relative to us, relative to the sun. but it's just the objects that are relatively nearby to us where we can actually perceive their motions. And so that's one of the main tricks that astronomers have used for a long, long time to discover things like new planets in the outer solar system, because you'll see the motion relative to the much more distant background stars and galaxies. And similarly, you can do the exact same process of looking for things that move as a key insight towards nearness for the closest stars and brown dwarfs. So yeah, as an example, this is what Barnard star, which I just talked about, a very nearby red dwarf, looks like when you blink images over, say, 10 years or 20 years. And its motion was discovered more than a century ago, and it still holds the record for the fastest known apparent motion of any star or brown dwarf, which I think is kind of remarkable. And as I was saying, this has been used not only for nearby stars, but also for planets in the outer solar system, although now we know that Pluto is a dwarf planet, not a true planet, at least according to the official definitions nowadays. So this is an example of the actual discovery images of Pluto, and those two little arrows point to its different locations spanning about a week of time. Now, I think it's a lot easier to see these types of motions when you blink two images in a movie type of style rather than looking at them side by side. Hopefully it's more apparent now that there's a little white dot that's moving near that, pointed to by that arrow, which is exactly how Pluto was discovered. In more detail, how Pluto was discovered is that there used to be these devices called blink comparators that people would use to blink between multiple astronomical images of the same part of the sky. So this was a really tedious and laborious way of doing astronomical research. I actually never used one of these before. I don't know if anybody in the audience has used one. Thankfully, nowadays we have the internet and computers, right? And so there's this transition from those relatively old school methods to things that can be done online. And so this is sort of my take on that citizen science, going from something that you do with your own hardware, like a telescope in your backyard. So this is Thomas Bob here, who I believe was in Arizona when he, as an amateur astronomer, co-discovered Comet Hale-Bopp in the 90s. And so for many years, when you thought of amateur astronomers, you would think of someone with their own rig in their backyard with a telescope in a place that has dark skies, looking at the sky. But now, with the rise of large data sets and the internet, I would say there's a much lower barrier to entry where anyone with an internet connection can use some of these online crowdsourcing platforms to get access to the data and to contribute to the science. So you don't need to have your own specialized equipment. You just need an internet connection and something like a tablet or a phone or a computer to work on. So one of these that's being shown here, these platforms, is called Zooniverse, which is very popular for doing astronomy, crowdsourcing projects, citizen science projects, or in other fields ranging from biology to genetics and history. So one thing that's been really impressive about citizen science in this age of big data has been the ability to make serendipitous serendipitous discoveries. I have no idea how long this train is supposed to last, sorry.
It's gonna be a minute.
At least the whistling should stop pretty soon. I think now you're good.
It seems to have faded into the distance at least a little bit. Yeah, so I was saying that one of the big benefits that's been seen over recent years using this big data crowdsourcing online approach to citizen science has been serendipitous discoveries of things that people hadn't really even known that they were looking for, but turned out to be extremely exciting astrophysical discoveries. So one example of this is what's referred to as Hanny's Voorwerp, which was discovered in 2007 by on the Zooniverse in this Galaxy Zoo project, it was called. And I believe this is a Dutch school teacher named Hanny van Arkel who discovered it. Another recent example of this would be Tabby Star, which you may have heard about in the press. It was discovered by the Planet Hunter Citizen Science Project in 2016. So what's shown here in this graph
Choo-choo.
So what's shown in here in this graph is the light from the star as a function of time, and it has these very odd, big, irregular dips in it, which many astronomers were quick to point out is exactly what you would expect if you had some sort of weird alien megastructure encircling the star. It was sometimes referred to as the WTF star, where's the flux? So eventually it was decided that something to do with dust explains this in a way that doesn't involve highly advanced extraterrestrial intelligence or anything like that. But it's still a great example of finding something really interesting that you maybe didn't ever expect to see through citizen science and crowdsourcing. So yeah, this brings me now to the Backyard World Citizen Science Project, which is a citizen science project that I co-founded in 2017. It's also run through this Universe Online crowdsourcing platform. Oh, whoops. I forgot that there was music on this, sorry. So yeah, I don't know if you can hear me with the music. But the basic idea is that we're going to look through this infrared WISE data set to see if we can find new planets in the outer solar system. Here we're just seeing the planets that are known in the solar system. Or eventually we'll also see brown dwarfs, which is another thing that we look for in backyard worlds. So yeah, this is an allusion to the fact that Pluto was demoted from being a planet to now being just a dwarf planet, just another member of the Kuiper Belt. So yeah, now we're zooming way out into the outer parts of the solar system, which is what we're trying to use citizen science to look for new planets out there. And then pretty soon it'll zoom out and show the local sun's neighborhood in the Milky Way to see the nearby stars and brown dwarfs. So right, as we go just beyond the outer reaches of the solar system, we now start to refer to that as the solar neighborhood, so like the local cosmic neighborhood of our sun. So the brown and red objects are meant to represent very cold brown dwarfs, and then the other objects here, like the white ones, are stars. All right, that was too loud for me. Maybe it's just me because I'm standing right next to the speaker. But anyway, you get the idea. We're using this citizen science approach with this NASA infrared data to look for nearby stars, nearby brown dwarfs, and also potentially hypothesized planets in the outer solar system. So now I just want to talk a little bit more about what we've been up to in the Citizen Science Project and some of the great contributions and discoveries we've been receiving from our volunteers, our participants. So you might ask, who are the Backyard World Citizen Scientists? And this is sort of a mosaic that we made showing that they span quite a range in age and quite a geographic diversity here. We have all over the US represented. We have lots of different countries, like I think France and Argentina at least are in here. And then we also have people ranging from college students to high school students to retirees. And so this alternate version of the mosaic shows some of the different occupations that they have: lawyer, data scientist, pulmonologist, you name it. All different backgrounds are coming in, which I think is really great for bringing different perspectives and helping us look at the same data in a different way and make new discoveries all the time. One thing that we found with Backyard Worlds especially is that when you run one of these crowdsourcing citizen science projects, it's not just equivalent to dumping a bunch of data online hoping people click on it. Like, there's a big community building aspect to it that will really take your project from just doing something to really making high impact discoveries and having a big impact on your participants' lives. And so one of the things that we do is that we always invite our volunteers to attend our weekly science team meetings with the professional science team. And this is a great way to get to know them, get feedback from them, also give them feedback on what they think are their most interesting discoveries that they bring to the table. What's shown here is kind of a fun moment where we took a screenshot. We realized that David here was calling in from his high school lunch period in the library. And so I thought that was great because I don't know what I was doing in lunch period in high school, but it definitely wasn't being on a call discussing science with professional NASA astrophysicists. So I think this is a really great way of bringing science to everyone. So here are some of the examples of what we've been discovering through the Backyard World Citizen Science Project. The idea here is that most stars and galaxies look like this normal black point of light color, but then the things in the middle, they have this distinctively orange color, and they're also moving, and that signifies that they're very nearby and very cold brown dwarfs. The other thing that we've been having a lot of success at finding is very cold companions to nearby brighter stars, and so you can see here that in each case there's one of these orange dots, but it's moving together alongside one of these much brighter objects. And so I really like these, they're called co-moving companion systems, because sometimes also called binary stars, although in this case not both components are stars. But I like to think of this as we're sort of witnessing the Planet X hypothesis, that scenario play out around other stars in our local solar neighborhood. Here's a nice 3D visualization that I like to show, which kind of presents some of the discoveries that we made through Backyard Worlds. We've discovered about 4,000 brown dwarfs so far. Not all of them are shown here. This is a 3D rendering where we're going around it basically. And then we'll see that all the objects pan out over time, because the way we discover them, right, is to look for them moving. And so we know their motions, and we know how this video is evolving over many, many millions of years. But we know how these objects will move and spread out across the galaxy over many, many millions of years, which is cool to think about. Here's another kind of cool 3D visualization. So right now we're in some imaginary spaceship coming in from on top of the Milky Way galaxy. The sun is not in the center of the Milky Way galaxy, right? It's in some outer spiral arm of it. And so here we're zooming in into the very local solar neighborhood that we're probing with Backyard Worlds Citizen Science Project, looking for these cold brown dwarfs nearby to us. And as we zoom in a little bit further, we start to see a bunch of these other normal stars that are more distant. That's what's being shown here that we're flying through. And then eventually you reach this white grid, which shows in detail the objects we've discovered. One other cool thing about this citizen science approach and this Backyard Worlds project is that we're taking discoveries that are made by the public, and we're actually able to get more detailed, what we call follow-up observations on some of the premier telescopes on the ground and in space. And so for Backyard Worlds in particular, we've used, for example, both of the Gemini telescopes in Hawaii and Chile, which are 8-meter telescopes. We've also used Hubble and Spitzer space telescopes, which are 2 of NASA's great observatories. And most recently, we've had success at winning time on the James Webb Space Telescope, JWST, to observe some of the objects discovered by our citizen scientists, which I think is amazing. So on the topic of JWST observations of objects that were discovered by the public through Backyard Worlds, this is one that I'd like to highlight, and it's a good example, again, of this concept of serendipity in citizen science and big data, where sometimes the best discoveries happen by accident. So this is actually our fastest moving discovery so far. The discoverer, who's a citizen scientist, he is a cybersecurity analyst for his day job. He nicknamed it the accident, which is now a term that we have used in the peer-reviewed literature. And so this is a highlight from an article in Quantum magazine that says, Dan Castleton was up late on November 3rd, 2018, playing the video game Counter-Strike when he made astronomy history. Every time he died, he would jump on his laptop to check in on an automated search he was running of NASA Space Telescope images. So it's a fun story, and it's a very scientifically impactful discovery, as evidenced by the fact that this object is now going to be set to be observed with some of the very precious and highly sought after JWST time. Just trying to anticipate questions that might come up at the end of this talk. What about artificial intelligence? Can't we just do this all with machine learning, with computers? And my take on this is that we shouldn't ignore the rise of AI and the rise of those systems like ChatGPT, Google Bard. I find those all very impressive and very useful. But I would pitch it as AI and citizen science can be complementary. These things can work together in a synergistic way to be greater than the sum of their parts. And so, for instance, what's called supervised machine learning often needs large training samples in order to know how to make predictions in the future. And so that type of training sample can be provided, for example, through crowdsourcing in this online manner, looking at a lot of data. I would also like to highlight that I'm running this new spin-off called Backyard Worlds Cool Neighbors, which was just launched earlier this summer, and it does something similar to what I just said, where we use the machine learning, the AI, to pre-select brown dwarf targets that are then shown to the volunteers online. So it's kind of like a way of leveraging the AI to make the time spent by our volunteers even that much more valuable and that much more impactful. So yeah, in the last few slides, transitioning into Agnes's talk, I just wanted to highlight briefly what Rubin Observatory is going to do for these fields of astronomy. And so Rubin will be a huge game changer for solar system astronomy, just because of the way that it surveys the entire southern sky many, many times over, and at each image, at each exposure, it goes very deep, very sensitive. And so Rubin is capable of detecting a single Earth mass planet as far away as about 1,000 astronomical units, which is 1,000 times the distance between Earth and Sun. So Rubin will really be able to either detect Planet 9 as hypothesized or rule out its being in the southern hemisphere in a way that no current existing data set is able to do. Rubin Observatory will also revolutionize the solar system much more generally than in terms of Planet 9. So over the entire course of all of astronomy, looking for asteroids, cataloging them, currently there's about roughly 1+ million asteroids that are known. And we expect that Rubin, just by itself, will discover another roughly 5 million asteroids. So it'll hugely increase, by a factor of 5 or 6, the census of asteroids in our solar system. And lastly, I did want to mention the plans for Rubin Observatory and citizen science. So citizen science is a major component of Rubin Observatory's plans that will really kick into action once Rubin Observatory starts flowing in its science quality data in a year or two. This is a huge data mining opportunity. If you think about it, I estimated something like 10 quadrillion pixels in the full Rubin LSST 10-year data set. LSST is kind of like the flagship 10-year survey of this Rubin Observatory telescope system. Something like 17 billion stars and 20 billion galaxies will be observed. For comparison, in this WISE data set, those numbers are like 500 million galaxies and 2 billion stars, roughly speaking. So this is a huge opportunity because this data is so great, it detects so much stuff, but it's also a huge challenge, right? Because now, if you're looking for one object, that one planet in the outer solar system, you have to sift through 20 billion stars and galaxies instead of 1 billion. I would claim that AI, supercomputers, and citizen science will all join forces together to help realize Rubin's full discovery potential. So, yeah, thank you.
Very much for that wonderful talk. You are free to take questions if you'd like. Just do me a favor and repeat the question for the live stream audience.
Yeah, I can take any questions, or we can take a break. I don't have a strong opinion about it.
You're going to follow up on the trivia question?
Should we follow up on the trivia question now or later?
Now.
Okay, does anybody know which is the only planet in the solar system that was discovered by a correct mathematical prediction? I see one hand raised, so I will call on the one hand raised.
Neptune.
Yeah, that's right.
Neptune?
Yeah, it was Neptune.
My question is, what are the hypotheses behind Planet 9?
Yeah, so like the question is what's the hypothesis behind Planet 9?
Yeah.
So you mean like what's the rationale behind it? Yeah, so there's these weird populations of outer solar system objects referred to as extreme trans-Neptunian objects that have that are kind of like, you can think of them as like being 100 or a couple hundred times further away from the sun than the Earth. And according to the people who support this Planet 9 hypothesis, they have some weird properties as far as they all cluster in certain ways. They're not totally randomly distributed as you might expect. And so the weird thing about these extreme trans-Neptunian objects is that they're essentially outside the influence of Neptune. They're too far away. They never get close to be influenced by Neptune. And so then the question becomes, what could possibly be out there that's sculpting these orbits of these extreme trans-Neptunian objects in such a way that they have these well-defined set of properties rather than totally random properties. And so that's the basic hypothesis, is that there needs to be some other large mass out there that's shepherding around these very distant trans-Neptunian objects. Now, every aspect of that hypothesis, that scenario, has been questioned at some point. Is the clustering statistically valid? Is it some selection bias, etc.? So it's kind of a point of controversy that some people are really, really gung-ho about this Planet 9 hypothesis, and some people just kind of shrug it off, even within the astronomical research community. Yeah, there's some that have been explored. I haven't personally been involved with them, but there were some thoughts that maybe, like, if you had very precise telemetry of some of these solar system probes, like Cassini, for example, that you could maybe infer that there's some other mass. I think at one point someone did an analysis which showed some sort of like tantalizing signs that Planet 9 was real, and then they were like, oops, we messed up on the telemetry analysis. So that's very typical of this whole situation, that it's fairly controversial, and there's people who are non-believers, let's say. So that's one other way. Another way is still fairly similar to what I've been describing, but basically you can look at very different wavelengths in the spectrum of light. So there have been thoughts about doing this with like radio observations, which are much, much longer wavelengths than anything I've talked about. So those are the main ones that come to mind, I would say. Or could you detect it somehow directly through its gravitational influence, or in some very different part of the electromagnetic spectrum?
More questions? Okay. One more round of applause for Aaron. Thank you very much. We're going to take a quick break, so we'll meet back here at 8:20. Like I said, in the meantime, come check out our merch table, get some drinks, tip your bartenders, and we'll see you in a few minutes.
Yeah, I mean, I've also been here for a long time, but I never come down here, so like, I probably should have known how to play trainer, but it's really just old. By default, I think it's showing. Over time. I kind of skipped over a lot. So I mean, I do talk to them, I do a lot of the work things I do, like the raw data. So that's fine. I'm going to be behind the scenes, so I don't know that. A lot of what I do is like the data the data straight off of the
Clicker? Jackie, camera's on this side. Perfect.
All right, everybody, we're going to get started again. Give you a set. Okay, so I'm going to take off my host hat and put on my news hat. It is time for the Astronomy Comedy Hour. I am normally joined by Danny Krolikowski, who is supposed to be at Kid Peak, so if you see him over here, no you didn't, it's just me. You can find me on Twitter as What a Merger Jr., and I'm going to teach you today about the Euclid telescope and the nanograv major announcement. So I'm not sure how many of you are here from the Rubin meeting versus just like general space nerds, so how many of you have heard of the Euclid telescope? Okay, great. An excellent fraction. Okay, it's okay if you haven't, because it's simply Europe's space race because they were jealous that JWST was American. Just kidding. We are very happy for the European Space Agency because a new optical and infrared telescope has joined the friendly skies of L2 after a successful launch on July 1st. Let's look at it. Okay, great. It spent 11 years in design and construction, which is actually fantastically fast. Given the fact that JWST was formally announced in 2002 when I was in second grade, I now have a PhD, so things take a while. Commissioning also takes a little bit. Choo-choo.
Choo-choo.
So with Webb, we had the amazing Christmas present of watching its launch in 2021, but usable data was not delivered until the following June. Similarly, Euclid... Similarly, Euclid is now in her troubleshooting era, so we'll let her finish that up before we come clamoring for new science. But here we are looking at some of the very first test images to come down from the telescope only a month after launch, so that's what you're looking at here. I'm normally very prepared for this, but I see that my next line is say something beautiful, blah, 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 so might be on that, but you can see with your own eyes how nice this is. So why do we have another visible and infrared telescope? Is it a red flag, an infrared flag even, that astronomers are so interested in them? Well, actually, Euclid has a fundamentally different construction and mission. It is meant to be a statistical surveyor. So it has a much wider field of view than JWST, and the intention is to gather images eventually over 15,000 square degrees, about 37% of the entire sky, over the course of its 6-year mission. For reference, it would take JWST hundreds of years to image the same area, and we really don't have time to wait, since given this summer's weather, the planet might not be here in a couple hundred years. Also, for the nerds, Euclid is equipped with two main instruments, the visible instrument, VIS, and the near-infrared spectrometer and photometer, NISP. VIS personally will never see the cloudless, bright, hellishly blue Tucson sky, not because of anything other than the fact that it's tuned to see green. And it has a mosaic of 36 CCD cameras comprising a 4,000 by 4,000 pixel image. It will be particularly useful in taking advantage of gravitational lensing, which is the phenomenon of massive objects like galaxies or galaxy clusters, bending the light around them to magnify more distant objects, and learn more about their shapes and colors. Once again, I've left myself with something, yo mama's so fat, she is a gravitational lens. The next instrument is NISP, which will enable 3D surveys to study the spatial distributions of galaxies across cosmic time. It covers 0.9 to 2 microns, so the Y, J, and H infrared bands, and it will be able to collect images through the photometer, or it can send the light through the spectrometry prism to obtain the ever-elusive spectrum that determines a galaxy's precise location and chemical makeup. Of course, no astronomical presentation would be complete without shouting that it will also solve dark matter and dark energy, but really that is only the start of what Euclid will be able to do. It's just that I've never seen an exoplanet before, and I know it can do things like that, but I don't know about things, so you have to go find someone else that does. So it has many non-galaxy use cases. It's humid for once, so I can't get my notes together. Okay, and we're back. Nanograph carries a result that's no nano weight. Shout out to the nerds in the room once again. I have gotten feedback in prior months that I do not include enough technical detail, which is surprising to me because the last thing I want to do after work is listen to someone tell me about science. But that's what you guys come here because it's not what you do all day, and that's great. And if it is what you do all day or you're a really big space nerd, you probably already heard about this back in June, but I was away last month, so now you can hear about it now. I am here to tell you today about the newest update in gravitational wave astronomy derived from the Pulsar Timing Array project called NanoGrav, the North American Nanohertz Observatory for Gravitational Waves. This is a project that has been underway for nearly 15 years and has now revealed a result so exciting it might spin you on your feet even hundreds of times per second and turn you into a pulsar. So let's back up. Let's talk about gravitational waves first. You might have heard of them back when they were detected at higher frequencies by the Laser Interferometer Gravitational Wave Observatory a few years ago, LIGO. Merging black holes create energy that sends waves through the very fabric of space-time, manifesting in the tiniest zoop-zip sound as black holes approach each other and eventually merge. You can Google zoop-zip gravitational wave and you can listen to it with your very own ears. Okay, so back to pulsars. How many of you have heard of pulsars? Great. Okay, so I'm preaching to the choir about, well, let's learn about them anyway. Stars a bit more massive than the sun, but not massive enough to collapse into black holes, are fated to become neutron stars, extremely dense cores of dead stars that have extremely strong magnetic fields. You'll often hear people say that a teaspoon of a neutron star weighs some insane comparison, I don't know, 10 billion Tucson trains or something like that, the entire human race, etc. But more interesting than those weight comparisons is that if one got...
Choo-choo!
Anyway, if we had a pulsar as close to the Earth as the moon is, it would instantly wipe every computer hard drive and every credit card on Earth at once. Sometimes I think we actually need a reset like that, so maybe we should try to harness a neutron star. So now neutron stars spin very fast with the classical lighthouse beacon effect. Every so often you will see a beam of radio light coming from the direction of its magnetic field. If you're not a space nerd, maybe you were dragged here by your cool girlfriend and you're just here for the ride, but you are a cool 80s music nerd, then you have seen pulsars before on the Joy Division Unknown Pleasures cover. So credit to Jocelyn Bell Burnell for discovering them, but obviously we give the credit to Joy Division there. And so their spins are so precise that they are considered the best atomic clocks that we have in the entire universe. And that means that any tiny deviation from the signal must be explained astrophysically. They should always be perfect. But if they move a little bit, that tells us something interesting. So using pulsars, we can detect the lower frequency counterparts to what LIGO was able to detect. So these are gravitational waves still coming from black hole binaries merging or possibly even merging neutron stars. And we do this by measuring teeny tiny deviations in the arrival times of these radio pulses, explained by the stretching and shrinking of space-time to a precision of 1 part per quadrillion. So you can see on this plot here that a straight line is the pulsar arrival time if there were no gravitational waves, and then this little visual zoop zip is the gravitational wave. So jokes aside, this is a huge result for the pulsar community, who have just been the sad radio people in many astronomy departments for many years, and they have been overlooked, and now it is their time to shine in radio wavelengths. They also do have to defend themselves against the usual crackpot theories that it's alien megastructures, cosmic strings, blah, 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 but we're pretty sure it's gravitational waves. And also they still have to defeat all of the people that think that we listen to radio telescopes like Jodie Foster and Contact, which of course we shot ourselves in the foot by calling them zoop zips. Well, I did that, but also you can listen to gravitational waves, so we kind of did that to ourselves. So that is the end of news this month. Sorry that Danny could not present to you, but we will be back in September with our full agenda. So time to put my host hat back on. Now it is time for our second talk of the evening. Thank you. So Agnès will be talking to us about the Rubin Observatory.
Thank you.
Clicker.
Hi. We'll wait for that one. Hi, thanks a lot for coming, everyone. And thank you for the team to accommodate us to talk this week. So I'm Agnès and I work at SLAC. I am a cosmologist, and one of the reasons why I am a cosmologist is because I grew up in the middle of nowhere in France, so I could see the stars at night. And of course, you start to ask yourself some questions about what is out there, what is space like. And of course, humans did that for many millennia from many cultures. And so they built observatories, and once we had telescopes since the 17th century, we started to realize that actually the sky is not just like tiny white blobs. It's actually planets, like in our own solar system, or planets outside of our solar system, rotating other stars, even binary stars, or like dead stars that leave some nebula. Or there is dust, or there is there are galaxies outside of our own galaxy, the Milky Way. And actually there are many galaxies. So we have built many observatories all over the world, and this is a map that you can check out online that shows the different historical and modern observatories. So right off the bat, here's a question for you. How many observatories are listed in this map? Is it A, around 100, B, 370, C, 540, or D, 980? Anyone wants to guess? Raise your hand. Yeah.
540?
Yes, that's right. Nice, well done. So I don't know how up to date it is, but yeah, that's an estimate of like 500, more than 500 observatories all around the world. And we like to put them high, where it's high and dry. And Noir Lab here in Tucson is one of the where Aaron works is an important place in the US for optical observatories. And nearby there is actually Kitt Peak. So yeah, I love telescopes. Like every time there is a telescope nearby, I need to go. So if I were you, I would totally try to go there. I don't know if you can like visit, but just check it out. No? I see no.
Not current. The fire last year caused some problems.
Okay. But check it out online or go see it from outside. Actually, in Chile right now, we're building a new observatory, the Rubin Observatory, on Cerro Pachon, which is a mountain near La Serena, north of Santiago de Chile. So it's being built right here on the top of this mountain near Gemini and other telescopes. Why are we building one more observatory when there are like 500 of them? We are building a fast 8.4 meter telescope that's going to be able to map half of the sky every 3 nights for 10 years. And I actually had the great opportunity to go and see the telescope last March. It's still in construction, but still it was amazing to see this, like it's a massive monster. I've seen big telescopes, like 10 meter telescope, but what makes it special is that it's compact. It's big and compact, so that makes it able to image the sky very fast. And it moves very quickly, which is almost scary when it starts pointing at you like that. To give you an idea of how big is the field of view of this telescope, this is a way to compare, where you see the Orion belt in the background and how it looks on the sky, and the Rubin Observatory telescope, the Simone telescope, will be able to image all of this in one go, in one exposure. And as a comparison, because most of you heard about JWST, but also it's a very different telescope with different science goals and actually very complementary goals. This is the field of view. It's 70 times smaller. So why did we build such a big telescope? So Aaron kind of convinced you that it's great to see moving objects, to detect new objects in the solar system. So with the Rubin Observatory, we will get a movie of the sky. So we will see things changing, either moving around or appearing, like stars dying and exploding, supernovae. And we expect millions of these things appearing or moving around per night. So that's a huge amount of data to analyze and figure out if we discovered something new. And in parallel, and that's what I'm interested in, we also will do deep and wide pictures of the sky. We will image billions of galaxies. And I will explain why we want to do this. So, the other reason why I'm doing cosmology is that when I was a teenager, I heard that the universe was expanding, and I was like, that doesn't make any sense. And actually, in undergrad, when I was learning about it, I still thought it didn't make any sense. I preferred a universe that was static and didn't evolve, because that's what makes more sense. Right now, I changed my mind. That's what makes the most sense. And actually, there are even weirder stuff happening out there. So this is not too hard to believe. So we have a way to describe our universe, which we call the lambda CDM model. It's a cosmological model. Because when you look at the universe as a whole, you can actually describe it very, very easily. So the universe has been expanding since inflation. And this discovery of the universe expanding was made 100 years ago. And since then, we've multiplied our cosmological data. And here, I just want to say that these are all different ways to observe the universe. With like data, which are those points with error bars. And the lines that you see that goes through them is all coming from the same model. So the same model is describing all of this different data. So we have our very simple way to describe our 13 billion years old infinite expanding universe, which I think is really incredible. But, okay, so this, when we look at on very, very large scale, on cosmic scales, this is what we think we will see, galaxies. But this is actually a very biased view of the universe. This is actually what it would look like. Indeed, galaxies are only the visible tip of big dark matter iceberg, of big dark matter structures. It's like galaxies are forming in cocoons of dark matter. So what is dark matter? It's 85% of the matter in the universe is this dark matter that doesn't emit any light. It actually doesn't interact with any force except gravity. And that's why we know that it's here, because we understand gravity very well. So we know where dark matter is, but we don't know what it is. And that's the goal of many experiments, but actually this is one of the bases of the Rubin Observatory, is to kind of map out the dark matter structures in the universe. Vera Rubin, in the 70s, was one of the first to confirm that dark matter existed, because she measured the velocity of stars rotating around galaxies, especially Andromeda, the galaxy closest to us, but also other galaxies. And she showed that stars that are far away from the center of the galaxy, where there is a more mass, are actually not, you would expect that they would go slower than the ones that are closer to this big mass. Like in the solar system, like Pluto or like Neptune, because Pluto is not a planet anymore, is going slower than the Earth. But actually, she showed that it's going way faster than we expected. So there is some more mass that interact gravitationally that is there. So that was the start of dark matter. So we take that into account in our model, and that's what we use to describe our universe. But that's not the weirdest thing. Because the universe is expanding, but for the past 5 billion years, it actually has been expanding faster and faster with time. That is not possible in a universe that's mainly made of matter, right? Because matter, because of gravity, will start to attract other matter and it's gonna slow down the expansion. But we see exactly the contrary in different, we have different data that shows us that the universe is accelerating. So what is causing this acceleration? We say that it's dark energy, which we explain by just a number in our equation. We call it the cosmological constant, lambda. And it would correspond to the energy of the vacuum. In space, if you go in the middle of nowhere, you would still have some energy. But the problem is, like, if you do the computation, like the theoretical computation, you actually see a mismatch of 10 to the power of 120 between what you observe, which is the biggest mismatch ever. There seems to be like a problem. We should do better than this, right? So the other alternatives are, is it not a constant at all? Or was Einstein wrong? And that's what I work on. Was Einstein's theory of gravity, general relativity, actually, which is one of the bases of our cosmological model, our way to describe gravity, is it actually not correct on cosmological scales? And or is it just a fifth fundamental force that would have like a repulsion effect on matter? And a way to solve this is to image galaxies, like Euclid, for instance, but with the Rubin Observatory, we're going to do that from Earth. So we're going to image galaxies, many galaxies, to probe this cosmic web of dark matter, to understand how it grows with time, so to understand the dark energy and gravity properties. And I actually dedicated the past like 10 years of my life to do exactly that, but with a precursor of the Rubin Observatory, which is a dark energy survey, which used the Blanco 4-meter telescope on the mountain just next to the Rubin Observatory. So it's kind of a very nice continuation. So actually I did most of this work at JPL during my last postdoc, and we tested gravity with the dark energy survey data. We didn't see any deviation from general relativity, but I really want to do more of that with the Rubin Observatory, because we will get more precise data, because we will have so many more galaxies over so much more sky. And I've shown that actually you can expect to test gravity 10 times better. So more chance to prove that Einstein was wrong. But in the meantime, we need to build this thing and to start to image the sky. So we all work together from, we are all around the world, and mainly in the US and Chile, working together on the Rubin Observatory to build it, to operate it, to analyze the data, to do the science. And we meet yearly in Tucson, and it's happening right this week. So if you see anyone else with those green t-shirts, you know that they come from the Rubin Observatory. They might be a bit stressed because there is so much to do, so say, "Go Rubin," or something like that when you see them. So we are finishing the observatory at the summit of Cerro Patron. So once it will be done, the dome will be able to open and to rotate so that we can look at the sky. The light from the sky is going to come through there. It's going to reflect on mirrors and then go into a camera, which will digitalize this light so that we can analyze it with computers and supercomputers. Every part of this telescope is incredible. So the camera that will digitalize the data is the largest camera ever built, with billions of pixels. So that's what it looks like. It's at SLAC right now, so I actually took this picture. And it's very impressive because actually this looks exactly like the length of a DSLR, but it's like my size. So it's really gigantic. So right now, that's why I'm saying that people are stressed. They're doing like the last few tests before shipping it to Chile during the fall. And there are a few lenses in front of the camera And the primary lens. Choo-choo.
Choo-choo.
I just want to say, I was very shocked by the volume of trains in the US. Because I took the train to cross the US last year and tried to sleep when this honks all the time. I think it's 100 decibels. I looked it up. There is a Wikipedia page about it. It's interesting.
Our train system is terrible.
I know, and I come from France, which has the fastest train, so it is different. It has its charm. So before the light gets into the camera, it's reflected by mirrors. And here again, it's absolutely incredible. The telescope is made of 3 mirrors. Usually it's like 2 mirrors, but this is 3 mirrors because we need all the light to be focused similarly over the whole focal plane, which is big. So the light will first reflect on this mirror and then onto a secondary mirror. This one is the largest convex mirror ever made. I think it's 3 meters wide. And then it will reflect into the third mirror. And so the primary and tertiary mirror are actually the same monolith, which I have never seen before, and I think it's really quite amazing. And again, cheers to Tucson, because the mirror lab here in Tucson made this big primary tertiary mirror, and they actually, so they took many years to make the mirror, grind it, polish it, make it the right shape, and they have all the technology to do that. They were done in 2015. And they actually have a lot of expertise, and they have been providing several 8.4 meter mirrors. For instance, the large binocular telescope, which is also in Arizona, and maybe try to check if you can see it, because it must be incredible. So these are some more pictures of how it looks like at the summit in this big building, because we need to stock things. Like this is the mirror cell. This is not the camera, but what it would look like. And what I was really impressed with, actually, is that there is this massive chamber, which is the coating chamber, where the mirrors, they need to be coated every few years so that they keep being reflective. So we will remove them from the telescope, put them in this chamber, and re-aluminize them. And this is like really big. I mean, it has to be more than 8 meters wide. So we have to ship all of this to the summit, like in this very remote area. I don't know about you, but when I ship things, it doesn't end up very well. Actually, the last time I sent something to France, it came back to me. We really don't want that to happen in the fall for the camera. So people have been working really hard on how to ship it. It's actually going to take the plane lands in Santiago and then go on a truck up there. In the past few years, they also have moved the mirrors. So that's the mirror in its container. This container is like 9.1 meter wide. On the way, there is a tunnel. Guess how wide? 10 meters wide. It was tight. But they did it. Now the mirrors, they have been at the summit for a while, actually. So it's all coming along very nicely. We are putting things together step by step. So overall, the Rubin Observatory will start imaging the sky in 2025, and I'm so excited because, first of all, because of dark energy and testing gravity, like we're going to test fundamental physics, but there are also things that we will probably discover things that we are not expecting at all. So I think you will have to come every year to hear from the Rubin people about the latest news. And actually, there is a lot of effort to do outreach, so you can follow this Twitter handle for more, or not Twitter, something else. Yeah, So we are super excited about this observatory, and thanks a lot for coming, and yeah, happy to take questions. Thank you. Any questions? Okay. I'll be around. So.
No questions? Not one? Okay, one more round of applause for our two wonderful speakers. So that is a wrap on Space Drafts number 90. We will be back the third Tuesday of September. You can check out our merch maybe for a few more minutes, and that's that. Thank you.
Woo!